Hi everyone, welcome to practical session number 2 for the Advanced Longitudinal Data Analysis Workshop at the American Congress of Rehab Medicine. I am going to be talking to you now a little bit more about expanding our models to actually build from a straight linear model into a curvilinear model, and then how to add interactions between our fixed effects at level 2 and our time variable at level 1. So Al has been talking about this in the lecture sections, and I'm going to be trying to kind of fill in the gaps here in the practical session. So we're going to be looking at our script file for practical session number 2, and you also want to make sure that you have the CSV file data_session2 saved on your computer, because we're going to want that in our working directory. Okay, so as before, like we did at the start of session 1, we're going to want to load the necessary libraries. Hopefully you don't get any error messages when you import those libraries. We can also check on our working directory. Mine's actually set up from the previous session still, so I still have that correct. But I am going to edit it here just so everyone can see what the appropriate working directory should be. And again, this is going to be slightly different on everyone's computer. So you can navigate to a folder in order to set that directory, or you can actually go into the menus within our studio and go to the session tab, and then within the session tab you can navigate down to your the working directory that you want. But it should be the same as whatever you had last time. So I can enter my working directory here. And the alternative, again, as I mentioned, would be you could come into the session tab and set the working directory from there to whichever folder currently houses your script files and data files. Okay, so I'm going to set my working directory, list files. We want to make sure that data_session2 is saved in there, and then we will import that data. And to start with, we just want to get a visual sense of what changing from a linear model to a curvilinear model actually means. So I've included some code for visualizing those different time effects. So first, we're just going to start with our traditional plot where we're looking at each person in each of the different AIS grades overall 18 months of therapy. And you can see this is generally not linear, right? We definitely have accelerated growth that then plateaus out and sort of flattens out following about 9 months in therapy. So we definitely think these aren't linear models, but then the question becomes, okay, if linear isn't going to be the best fit, what is ultimately the best fit? So in this session, we're going to be exploring curvilinear models. Truly nonlinear functions are possible. They're a little more complicated. So we're going to focus on building curvilinear models, which should be a very good approximation of this kind of curve, even though you could arguably get a better fit, potentially, with a nonlinear model in different cases. So first, let's actually look at what our linear model predicts. So this is similar to what we did in session number 1. We were estimating a linear model for each person. So here we've run the code to create a subset of the data. We're looking at individual data for 6 participants, right? So those are in the 6 windows. Each subject's data points are color-coded and then connected by dark lines. And then the linear estimate is represented by the blue line that runs through each participant's data. And you can see that the linear estimate isn't terrible, right? You know, people definitely improve over time, and that's captured by the linear function, but it's not a particularly good fit, especially early on in therapy where the Roche-scaled FIM scores are changing at an accelerated rate. It's going to be a much better fit later on in therapy where things have actually started to level out a little bit. So let's see if we can expand on this by going from a linear model to a quadratic model. So you can see this in the code where we have changed the formula now to be y as a function of x and x squared. So we're going to have both linear time as x and time squared as the quadratic. And now we should see a nice curve to our data. So you can see that that does actually improve our model fit visually quite a bit, right? These data are curved. For some people, it's still not quite as good an approximation because you can see for subject 1, there's some pretty substantial deviation away from the quadratic prediction at the beginning. For subject 4, it seems like a pretty great fit, right? Their data follow the quadratic model pretty well. We can take this a step further by, again, making our formula more complicated and adopting a cubic model. So we're going to have y as a function of x plus x squared plus x cubed. And this cubic model will allow that curved line to actually plateau out a little bit more, if you recall sort of how a cubic function looks. And we can plot this again to the window. And you can see that this actually has enhanced our model predictions even more. We have a better correspondence between the data and the model's predictions for almost all of our subjects. Again, for subject 4, this is a really great fit. Subject 1 is a little more problematic given their accelerated change at the beginning. And there is still some variability, right? But in general, just sort of visually inspecting these data, it seems like a cubic model is going to be a better explanation than the linear model. And the question is then, okay, is the cubic model also a better explanation than the quadratic model? Because we don't want to build models that are unnecessarily complicated, right? We sort of want the best trade-off between model complexity and explanatory power. So in order to do this, you might recall from session 1, we transformed our months variable into a years variable, and specifically we had year.0, where the first data point was fixed as 0. Now we're just going to create quadratic and cubic versions of that same variable. So I'm going to create year.0 squared and year.0 cubed. And then we're going to build 3 different models, and we're going to add a fixed effect and a random effect in each one. So we're going to call this first model time linear, where we have a fixed effect of year.0 and a random effect of year.0. Then we can print that model to the screen to see what it looks like, and you can see that there's our fixed effect. The linear effect of time, as before, is statistically significant. Then we'll build our quadratic model. So again, we're going to add a fixed effect. So we're going to add a fixed effect for year squared. Then we're also going to add our random effect. So we'll add a random effect of year squared to this model. We'll print that to the screen. You can see that this changes our estimates, for instance, of the linear effect quite a bit now that we have the quadratic effect in there. But they are all statistically significant. So next we want to build our model with the cubic effect of time. So we're going to look at Roche-scaled FIM scores as a function of fixed effects with both the linear effect of time, the quadratic effect of time, and the cubic effect of time. And then in our random effects, we'll also have all 3 of those values. We'll have random effects for the linear, quadratic, and the cubic effect of time. Then we can go ahead and run that model. And you'll notice that we get a warning message. Not an error message, but a warning message. So R will still actually give us a result here, but it wants us to warn us about something that's going on. And it says, unable to evaluate scaled gradient, and model failed to converge degenerate Hessian with 1 negative eigenvalues. So what's going on here, we can get to sort of a more computationally complex explanation or a more general explanation. And the statistically detailed explanation, I think, is very important. We won't get into it here, in part because I can't speak to it super intelligently. But I think the thing, when you see this warning about the model failing to converge, you have a degenerate Hessian with -1 eigenvalues. What's going on there is that your random effect structure is probably too complicated. The model is effectively running out of the degrees of freedom it needs to estimate all of the fixed effects, random effects, and the correlations between random effects that we have in our model. And we might be sort of reaching a saturation point in that correlation. We might have some extremely high correlations between our random effects. So we can actually see that if we print this model to the screen. And again, you can see the warning message being appended down here at the bottom. But let's scroll up to look at our random effects here. So you can see that we have random effects for the intercept, the year, linear year, quadratic year, and the cubic year. We have variances for each of those. Then we can look at the correlations between these random effects as well. The quadratic and the cubic effect are very highly correlated with the intercept, and the quadratic and the cubic effect are very highly correlated with each other. So part of that probably also relates to the way in which we coded these variables, because we centered time at 0 rather than centering time in the middle. That potentially is inducing this collinearity between these random effects. But the issue is also that we have quite a few random effects, and this is actually a fairly complicated structure. I think this model actually has about 15 degrees of freedom if we look at it in the model comparison. Right, so you can see, yeah, so we have 15 degrees of freedom. It does give us the best AIC, and the change in the deviance is significant. So even though we get this warning message, right, and we still get an answer from R, but the warning message is concerning, and it probably means that we could define a simpler model that isn't going to generate this error. And again, I think kind of the most concise explanation of this is that your random effect structure is getting too complicated. So down below, we're actually going to rerun the same model, but we're going to have a fixed effect only for the cubic value. So we're going to have fixed effects, we're going to have fixed effects for the linear, quadratic, and the cubic, but we're going to have no random effect of the cubic. So in our random effects, you can see we've got the linear year and this quadratic year, but we've gotten rid of that cubic year. So we're going to create this new model called time cube fixed. You see that we don't get any error messages there. And then we can compare time cube fixed to time cube. And time cube fixed actually produces a lower AIC value than time cube. So by removing that random effect, we've saved ourselves 4 degrees of freedom, and it ultimately is a pretty comparable explanation of the data. So what this is suggesting is that our cubic effect is very similar for pretty much everyone in the model, and adding that random effect of year cubed isn't really getting us a lot of explanatory power. So we're better off just ignoring that random effect for time cube and sticking with our fixed effect for the cubic value of time. Okay, so that's a lot to process, but ultimately I think we've come to the conclusion that we have a really good shape model for the shape of time if we have a cubic, up to a cubic fixed effect, but we go only up to the quadratic random effect, and we seem to be accounting for the individual differences in our data pretty well, and then we're explaining those random effects well with the fixed effects of time. In the next series of models, we want to look at conditioning conditioning the fixed effects on the AIS grade for our different participants. So to start with, we're going to create a conditional model in which we make the linear effect and the intercept conditional on AIS grade. So this is equivalent to what we did back in session 1, right, where we had effects of AIS grade on the intercept and the slope. But for now, we aren't going to have effects of AIS grade on the quadratic or the cubic effects. All right, so we can run that model, and we get an explanation of the data here. We can see the fixed effects now are getting more complicated as we're adding in these interactions with our different time parameters. We can also then add the effects of AIS grade to the quadratic effect of time. And we can print that to the screen. Now it's getting more complicated, right? So we can see here's all of our fixed effects, and again we'll unpack these once we kind of decide on our best fitting model. But we want you to look at the effects of year with AIS grade and the effects of year squared with AIS grade. And then in our third model, we'll add in cubic interactions. And now we can see it's gotten significantly more complicated, but you can see that once we get down to AIS grade interacting with the squared effect of year, we don't seem to get any statistically significant contrasts. So of course, before we actually go in and unpack these individual statistical tests, let's look at the omnibus tests for the overall model. And of these conditional models that we built, the lowest AIC is actually for the first one by about 3 points. Okay, so the first model, in which we have linear, quadratic, and cubic effects, but AIS grade only interacts with the linear effects, is probably the best explanation of the data. So let's go back to that model and take a look at it. All right, so when we're now looking at this model with our interactions only for the linear effects, we can interpret some of these parameter values. And again, remember that R uses treatment coding, or what some people would call dummy coding, where there's one reference group, and then the other values are defined with respect to that reference group. So we have an intercept, and we have year.0. So that's the intercept and the linear effective time for people in AIS category 1 to 4. We also have the year squared and the year cubic, and those are the quadratic and cubic effects of time for people in AIS grade 1 to 4. But now, because this model doesn't include interactions between these parameters and AIS grade, these also then generalize to the other groups. These are the main effects of the squared effective year and the cubic effective year. But the linear effective year does actually change depending on if you're in group C5 to 8 or if you're paraplegic. So in comparison to grades C1 to 4, the grades C5 to 8s have a slope that's about 4 points higher than the reference group. And the paraplegic participants tend to have a slope that's about 6.9 points higher than our participants with grades C1 to 4 injuries.